When most Americans think of a mountain range, we think of the Rockies or the Appalachians, vast, silent monoliths that feel as permanent as the planet itself. We treat them like the ultimate foundation, the bedrock of our geographic identity. But if you're an engineer standing in the Riasi district of Jammu and Kashmir, looking up at the jagged teeth of the Himalayas, you realize very quickly that everything you thought you knew about solid ground is a lie. You aren't looking at a monument, you're looking at a slow-motion disaster. The Himalayas are the youngest mountain range on Earth, and in geological terms, they are essentially a massive, unfinished construction project that nature forgot to clean up. They are young in the way a hyperactive toddler is young, constantly moving, prone to tantrums, and incredibly destructive. While the mountains of the American West have had tens of millions of years to settle into their middle age, the Himalayas are still growing, still shifting, and still trying to figure out where they want to sit. And it's right here, in the middle of this tectonic mosh pit, that India decided to build the Chenab Bridge. To give you a sense of the scale, we aren't just talking about building a bridge. We're talking about pinning 30,000 tons of high-grade steel to a canyon wall that is effectively made of smashed biscuits. In the States, we're used to the Big Dig, or the replacement of the Bay Bridge projects, defined by bureaucratic red tape and astronomical labor costs. But the challenge of the Chenab wasn't just financial or political. It was a fundamental argument with gravity. The Chenab River carves a deep, violent V-shape through the landscape, creating a canyon that looks like a masterpiece on a postcard, but acts like a death trap for anything made of concrete and steel. The problem isn't just the height, though. At 1,178 feet, it's taller than the Eiffel Tower. It's the fact that the ground you're standing on is actively trying to slide into the river below. This is the moving mountain problem. It's what happens when human ambition meets a geological force that doesn't recognize the concept of a finished project. To understand how they pulled this off, you have to stop thinking of the Earth as a platform and start seeing it as a living, breathing, and very angry opponent. To understand why this ground is so unstable, you have to look at the global map of tectonic violence. Imagine the Indian subcontinent as a massive, geological semi-truck, traveling north at about 2 inches a year. That doesn't sound like much, until you realize we're talking about a landmass weighing quadrillions of tons. About 50 million years ago, that truck slammed into the Eurasian plate. In a normal car crash, the hood of the car crumples. In a tectonic crash, the Earth's crust buckles into the sky. That's how you get the Himalayas. But because this collision is still happening, the mountains haven't had time to set. They are under constant, unimaginable pressure, which does something terrifying to the internal structure of the rock. In the United States, our infrastructure is often built on the old reliables, the stable granite of the Northeast, or the massive limestone slabs of the Midwest. Even when we build in earthquake-prone California, we're dealing with faults that have somewhat predictable patterns. But in the Chenab Canyon, the rock is what geologists call friable. In plain English, that means it's brittle, it's flaky. It's the kind of rock that looks like a solid cliff face from a distance, but if you hit it with a hammer, it shatters into 1,000 pieces like a dry biscuit. This creates a nightmare for civil engineers. Usually, when you build a bridge of this scale, you want to find competent rock, the kind of stone that can take the massive downward pressure of a bridge's weight and spread it deep into the earth. But at the Chenab site, the rock is so fractured by millions of years of tectonic grinding that it's less like a foundation and more like a pile of loosely packed rubble. Think about the sheer audacity of that for a second. The Indian government didn't just decide to build the world's highest railway bridge. They decided to do it on a slope that is essentially a vertical landslide waiting to happen. If you tried to build a skyscraper on a foundation of loose gravel in downtown Manhattan, you'd be laughed out of the permit office. In the Himalayas, that wasn't just the challenge, it was the baseline. The engineers were forced to play a high-stakes game of operation, where one wrong move wouldn't just result in a buzzing noise, but in 30,000 tons of steel sliding 1,100 feet down into a churning river. But the crumbling rock is only half of the equation. Once you step out into that canyon, you aren't just fighting the ground beneath your feet, you're fighting the very air around you. In the world of fluid dynamics, there's a phenomenon called the Venturi effect. Imagine you're watering your garden, and you put your thumb over the end of the hose. The water speeds up because you've restricted the space it can flow through. Now, apply that same logic to a Himalayan canyon. The Chenab Canyon acts like a giant, natural funnel. When those high-altitude winds hit the mouth of the valley, they have nowhere to go but through that narrow gap. The air is compressed, its pressure drops, and its velocity skyrockets. We're talking about gusts that can hit 165 miles per hour. To put that in perspective for an American audience, that's a Category 5 hurricane. Now, imagine trying to build a bridge not in a hurricane, but inside a permanent hurricane machine that sits 1,000 feet in the air. For the 30,000 tons of steel that make up the bridge's arch, this wind isn't just a nuisance, it's a structural threat. A bridge of this size acts like a giant sail. If the wind hits it with enough force, it creates lateral pressure that wants to twist the entire structure right off its foundations. And remember, those foundations are anchored into that biscuity rock we talked about. It's a mechanical nightmare. The wind is trying to push the bridge over, while the mountain is trying to let it slide down. Then there's the issue of slope failure. In the States, we see this often along the Pacific Coast Highway in California. One heavy rain, and the hillside decides it wants to be at sea level. In the Himalayas, the slopes are steeper, the rock is weaker, and the stakes are much higher. A bridge usually relies on vertical gravity, weight goes down into the ground. But because the Chenab is an arch bridge, it relies on horizontal thrust. It's literally pushing outward against the canyon walls to stay up. It's like a person standing in a hallway and pushing their hands against the walls to keep from falling. If those walls are soft or unstable, the whole thing collapses. The engineers were essentially trying to brace a massive steel giant against a wall made of moving sand. So, how do you stop a mountain from moving? In the United States, when we have an unstable hillside threatening a highway, we might throw up a retaining wall or a mesh net and call it a day. But when you're dealing with the lateral thrust of the world's highest arch bridge, you need something more than a keep-out sign for falling rocks. You need what I like to call engineering duct tape on a massive industrial scale. The solution was a process called rock bolting. But calling it a bolt is like calling a Saturn V rocket a firework. To stabilize the canyon walls, crews had to drill thousands of deep holes directly into the fractured Himalayan face. Into these holes, they inserted high-strength steel cables and rods, some stretching over 150 feet deep, and then pumped them full of specialized grout. Once the grout cured, these bolts were tensioned, essentially cinching the mountain together. Imagine taking a stack of loose, flaky pastry and driving a series of long toothpicks through it until it becomes a solid block. That is what they did to the Himalayas. They didn't just stop at a few bolts, either. We're talking about an entire subterranean forest of steel. On the Kauri side of the bridge, the north bank, the geological conditions were so precarious that they had to build a massive concrete plug inside the mountain itself just to give the arch something to bite into. This wasn't just construction, it was a surgical intervention. This technique is a far cry from the way we often approach infrastructure in the West, where we prefer to blast away the bad parts and build on what's left. In the Riasi district, there was no good part to find. The engineers had to accept the mountain's flaws and essentially rewire its internal physics. They turned the mountain from a crumbling liability into an active structural component of the bridge. It's a brilliant, if slightly terrifying, workaround. The bridge stays up because the mountain is being forced by thousands of miles of steel cable to hold onto itself. It's a testament to the idea that if you can't trust the ground, you have to find a way to make the ground trust you. If the wind and the crumbling rock weren't enough to keep an engineer awake at night, there's the constant threat of the ground simply disappearing beneath you. The Himalayas aren't just shifting, they're shaking. This region sits in seismic zone V, the highest possible risk category in India. For an American viewer, that's like building a skyscraper directly on top of the San Andreas Fault, then inviting the most volatile parts of the Cascadia subduction zone over for a housewarming party. In the West, our traditional approach to seismic engineering has often been strength through rigidity. We build thick concrete piers and massive steel beams, designed to muscle their way through a quake. But if you build something that rigid in the Himalayas, the mountain will simply snap it like a dry twig. The Chenab Bridge required a total shift in philosophy. If you can't beat the earthquake, you have to learn how to dance with it. Engineers designed the bridge to be seismically transparent. This sounds like marketing fluff, but it's actually a brilliant bit of physics. Because the bridge has such a massive span, nearly 1,550 feet across it, actually possesses a natural period of vibration that is much longer than the rapid, violent shaking of the ground during a typical earthquake. Imagine a giant bell. If you hit it with a small hammer very quickly, The bell doesn't really swing, it just vibrates. In the same way, when the ground starts oscillating by 10 or 20 centimeters, the bridge is so massive and its swing is so slow that the relative effect of the shaking is actually diminished. But it's not just about the size. The bridge is packed with sophisticated dampers and modular expansion joints that allow the deck to slide and breathe. If a massive quake hits, the bridge doesn't just sit there and take the punch, it shifts. It absorbs the energy through controlled movement. This stands in stark contrast to how we've historically managed the infrastructure gap in the U.S. We tend to over-engineer for the big one by making things heavier and more expensive. In Kashmir, they realized that weight is the enemy. By making the bridge flexible, they ensured that while the mountains around it might crumble and the roads might disappear, the arch itself will remain standing, a lonely steel survivor in a landscape that refused to sit still. If the bridge is a dancer during an earthquake, it becomes a living, breathing organism under the Himalayan sun. For most Americans, a 50-degree temperature swing is a seasonal change from a crisp fall morning to a humid summer afternoon. But at the Chenab site, those temperature swings aren't seasonal, they're daily. The thermometer can plummet toward freezing at night, and then skyrocket to a blistering 122 degrees Fahrenheit, 50 degrees Celsius, as the sun hammers the canyon. When you're dealing with 30,000 tons of steel, heat isn't just a comfort issue, it's a measurement nightmare. Steel is a material with a high coefficient of thermal expansion, meaning it grows when it's hot and shrinks when it's cold. On a bridge this size, that expansion isn't measured in millimeters, it's measured in feet. If you simply bolted the rails down to a rigid deck, the heat of the afternoon would cause the tracks to buckle and warp, turning a high-speed rail line into a roller coaster that would derail a train in seconds. The solution was a masterstroke of pre-stressed engineering. The engineers didn't just lay the tracks, they pulled them. By putting the rails under massive amounts of tension before securing them, they ensured that the steel already occupied the space it would naturally want to expand into. But the real genius lies in the fixings. Instead of being locked into place, the rails sit in specialized chairs that allow them to slide back and forth independently of the bridge structure. Think of it like a giant trombone. As the bridge arch warms up and flexes bending under the thermal load, the rails stay straight, sliding through their brackets like a slide whistle. This floating rail system is a direct response to the moving mountain problem. Since you can't stop the mountain from shifting, and you can't stop the sun from expanding the steel, you have to design a system where every component has permission to move. In the U.S., we often see our infrastructure as a battle of man over nature. But here, the win wasn't found in dominance, it was found in the give. The bridge works because it knows how to get out of its own way, allowing the laws of thermodynamics to play out without tearing the tracks apart. Ultimately, the Chenab Bridge is more than just a trophy for India's engineering sector. It's a case study in what it takes to build for a future that refuses to stay put. For an American audience used to seeing infrastructure as a static, set it and forget it investment, the Chenab is a wake-up call. It proves that the era of building on solid ground is over. Whether it's the rising sea levels threatening the Florida coast or the unstable tectonics of the Himalayas, the environment of the 21st century is in a state of constant flux. The moving mountain problem teaches us that resilience isn't found in the thickness of your concrete or the weight of your steel. It's found in the intelligence of your design. We've spent a century trying to pave over nature's problems, but the engineers in Kashmir didn't have that luxury. They had to build a structure that could breathe with the temperature, dance with the earthquakes, and cling to a crumbling cliffside like a rock climber. As we look at our own aging bridges and crumbling highways back home, the Chenab stands as a reminder that impossible is usually just a lack of imagination. It took 20 years of donkeys, cable cranes, and millions of man-hours to pin this arch to the sky. But the result is a bridge that doesn't just cross a canyon, it survives a continent. It is a monument to human hubris, yes, but also to human humility. It's the realization that if we want to build something that lasts, we have to stop fighting the earth and start learning how to move with it. In the battle of geology versus gravity, the Chenab Bridge didn't pick a side. It simply built a way through the middle.